Now, two results in the form of two theorems are very much useful in solving a question using algebraic method. The first one is, let exy be the expectation function of an m plus n rectangular game. Now suppose that we have x star a mixed strategy for p1, a y star is a mixed strategy for p2, and b is a real number. Then an assertion sufficient condition for x star to be an optimal strategy for p1, y star to be an optimal strategy for p2, and v to be the value of the game is that ei y star is less than or equal to v is less than or equal to e x star j for all i's in I and j in j. In fact, if x star is an optimal strategy for p1, y star is an optimal strategy for p2, and v is the real number and v is the value of the game, then this holds, and vice versa. Now, this theorem or this result tells us that let's find some x star in Sn, a y star in Sn, and a real number v which satisfies this one. Then by this result, what will happen? This x star will become an optimal strategy for p1, y star will become an optimal strategy for p2, and v will be the value of the game. This precisely helps us in writing the linear programming equivalents of a game. And the second theorem is, let exy be the expectation function of a game whose value is v, and let x star in Sm and y star in Sn be optimal strategies for p1 and p2 respectively. Then by the previous result, we will definitely have ei y star less than or equal to v, e x star j will be greater than or equal to v. Now suppose for some I in I with ei y star less than v, then we must have xi star equal to 0. Likewise, if for some j in j we have v less than ex star j, then it must imply that yj star will be equal to 0. The two theorems collectively gives us the method, the way to solve any rectangular game of any size. Now let's solve this question using algebraic method. It's a 2 cross 3 matrix over here. Now in view of theorem 1, we need to find an x star equal to say x1, x2 in S2. Here we have x1, here we have x2 for b1, of y star equal to y1, y2, y3 in S3, like here for p2, and a real number v, so that ei y star is less than or equal to v is less than or equal to ex star j for all I varies form. Look, I can take the values 1 and 2, and for all j's, j can take the value from 1 to 3. That is to find x1, x2, y1, y2, y3 and v, so that e I y star, so let's take I equal to 1 first, y star, this means that this is equal to e1 y star will be 2y1 plus 3y2 minus y3. This should be less than or equal to v. E2 y star is equal to 3y1 from here plus 2y2 plus 6y3. This should be less than or equal to v. Now where this y star should belong to S3, so we must have that y1 plus y2 plus y3 equal to 1, and y1, y2, y3, each of these should be non-negative because it belongs to S3. These are frequencies over here. Now their sum equal to 1 ensures that each of 1 will lie between 0 and 1, and E x star 1. Now x star is over here, so with 1 it will be like this one, 2x1 plus 3x2. 2x1 plus 3x2 less than greater than equal to b. E x star 2 equal to 3x1 plus 2x2 greater than equal to b. E x star 3 will be minus x1 plus 6x2 greater than equal to b. Now again, this x1 plus x2 should be equal to 1 and x1 and x2 should be non-negative because this x star belongs to s2 over here. Now we'll solve this system over here. What we do? We take first all equalities over here, equal to 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 here, and try to solve these systems with these conditions over here. Now if this system has a solution which satisfies all these ones, then that will be a solution to this game over here. Then that particular x star with x1 and x2 and y star, y1, y2, y3 and v will be the optimal solution for the game. Now in case this system doesn't have a solution with equalities, what we do? We take one of these inequalities as inequality. Say here, we'll consider that system for which e1 y star is less than v. This equal to v, this equal to and equal to over here. And then because y1, y2, y3, that is y star, is going to be an optimal strategy for p2, so we must have, because this first one is satisfied as inequality, so we must have definitely x1 equal to 0. So we'll take up x1 equal to 0 in that case. So we'll solve that system. Now in case it has a solution, it's okay. Otherwise, what we do? We shift this inequality over here. We take this as equality and this as less than over here. Likewise, over here in that case, x2 will be 0. And thereafter, we'll solve this system. Now in case it has a solution, that will be a solution for the problem. In case it doesn't have, then we'll shift this inequality over here. We'll have here strict inequality greater than, whereas all others will be treated as equalities over here. Equality here, equality here, equality here, equality here. Now this greater than means that y1 will be 0. We'll solve this system here. In case it has a solution, then that will be an optimal solution for P1. In case it doesn't, we'll shift this inequality over here. Again, we'll try to solve it. In case it has, then that will be solution. In case it doesn't, we'll shift this over here. And likewise, these will be equal over here. And then for this, y3 will be equal to 0 because of our second result. And consequently, we'll get the solution over here. Now, in case it doesn't have, then we'll start taking two inequalities over here. One here, one here. Then one here, one here. One here, one here. Likewise, so many systems we need to solve in order to find the solution of this one. And we are not sure which system will have a solution. The moment a system will have a solution, we'll stop there and we'll have optimal strategies for P1, for P2 and the value of the game. Let's recall what we have done so far. We consider a rectangular game and then we had the methods to solve the rectangular games. The very first one was to check whether the rectangular game has a saddle point or not. In that case, max min should be equal to min max. In case that is there, then it's done. Now in case the game doesn't have a saddle point, then we move to solve a game with 2 cross 2 as the payoff matrix. In fact, it's a little bit of Algebraic method over here. And then we shifted to the relations of dominance to come to the bigger games. Relations of dominance we use to reduce the size of the matrix, and thereafter again making use of 2 cross 2 games over there, the method of 2 cross 2 games over there. And then we have graphical method. This graphical method has its own limitations, can be applied to the games with size 2 cross n or m cross 2 over here. But we have this algebraic method, can be applied to any game of any size, say it's an m cross n. Only problem is that this one is little bit lengthier process. That's why people avoid using this one try to make use of as these ones as much as possible. But this algebraic method is the strongest among all these ones. It can solve any game of any size. And likewise, based on theorem 1, the previous result in the algebraic method, we have equivalence of a game to its pair of linear programming problems. We can convert a game into linear programming problems which further can be solved using simplex method. Now over here we are going to learn how to convert a game into linear programming problems. We are not going to solve these ones, can be solved using simplex method, and then the results, the value of the game can be obtained. The optimal strategy for P1 and P2 can also be obtained by little bit of manipulation. Let's have equivalence of a game to its linear programming problems. We can convert a game into a pair of linear programming problems, and we'll illustrate this with an example over here. Let's have this as an example, but give the linear programming formulation for player A as well as of B for this game over here. Now, in order to convert a game to its linear programming problem, we have to ensure that our V should be positive. The value of the game should be positive. Now look at this. For that, we need to find max, min and min max over here. Let's find out minimum over here is 1, 0 and 2. And so, max min will be equal to maximum of 1, 0 and 2. And over here, for the columns, the maximum will be 9 here, 6 here and 8 here. So min max will be equal to minimum for all these will be 6. So V will lie between max min and min max. Max min is 2 and 6. This V greater than or equal to 2 ensures that V is greater than 0. So we are not supposed to do anything over here with this matrix, otherwise we need to change this matrix. Now in view of theorem 1, solving this game means to find an x star equal to x1, x2, x3 in S3, or y star equal to y1, y2, y1, y2, y3 in S3 and a real number V such that EIY star is less than or equal to V is less than or equal to EX star J. Now if we could find such X star and Y star and a V, then what will happen? By theorem 1, X star will be an optimal strategy for P1, Y star will be an optimal strategy for P2, and V will be the value of the game. Here I and J both are same. They belong to I equal to J equal to 1, 2, 3. Now let's write all these ones over here. This is for P2, whereas this is for P1 over here. That is to find x1, x2, x3. The optimal strategy for P1 over here would be y1, y2, y3 for P2 and V such that EX star 1. Now what is EX star 1? It involves x star and 1 from P2 sorry. So it will be 9x1 plus 0x2 plus 5x3. This should be greater than or equal to V. Likewise, EX star 2 will be x1 plus 6x2 plus 2x3 greater than or equal to V. 4x1 EX star 3, 4x1 plus 3x2 plus 8x3 is greater than or equal to V. Now where this x star should belong to S3, so this sum should be equal to 1, and each of these x1, x2, x3 should be non-negative. Likewise, we have E1 y star. It means 9y1 plus y2 plus 4y3. This should be less than or equal to V here. 0y1 plus 6y2 plus 3y3 should be less than or equal to V, and E3y star finally 5y1 plus 2y2 plus 8y3. This should be less than or equal to v. Again, y sub belongs to S3, so their sum should be equal to 1, and each one of these should be non-negative. Now, dividing all these relations, because our v is positive, look here that v is positive is being used. Because our v is positive, so we divide all these relations by v over here and over here, and then writing, let's divide it. We'll get here 9x1 by v. Let me write x1 by v as x1 dash. So I'll get here 9x1 dash plus 0x2 dash, we are going to write nothing, 5x3 dash is greater than or equal to 1. x1 dash plus 6x2 dash plus 2x3 dash greater than or equal to 1. 4x1 dash plus 3x2 dash plus 8x3 dash greater than or equal to 1. And then we have here also x1 dash plus x2 dash plus x3 dash equal to 1 by v. And finally, with these non-negative restrictions, it will be non-negative restrictions, it will be x1 dash, x2 dash, x3 dash greater than or equal to 0. We have divided all the relations by v, where what is x1 dash is equal to what is xi dash equal to xi by v. I varies from 1 to 3 here, and we get here, we need to divide these relations also by v. We get here 9y1 dash plus y2 dash plus 4y3 dash less than or equal to 1. 6y2 dash, the first one will be 0, plus 3y3 dash should be less than or equal to 1. 5y1 dash plus 2y2 dash plus 8y3 dash less than or equal to 1, and then y1 dash plus y2 dash plus y3 dash should be equal to 1 by v. y1 dash, y2 dash, y3 dash, they are all greater than or equal to 0, where what are yj dashes? These are equal to yj divided by v. J varies from 1 to 3 over here. Since player A would like to maximize v because he is going to earn, so for player A, the problem is to maximize v, that is to minimize 1 by v. So the player A will minimize 1 by v, that is what is 1 by v is x1 dash plus x2 dash plus x3 dash subject to these constants over here, where each xi dash, x1 dash, x2 dash, x3 dash will not equal to 0. Likewise, the player B would like to minimize his payoffs, that is would like to minimize the value of the game B, that is player B would like to maximize 1 by v subject to these constants over here, these ones, along with these non-negative restrictions. Hence the player A would like to maximize v means minimize 1 by v equal to x1 dash plus x2 dash plus x3 dash, just subject to these constants here. This problem P is the linear formulation for the player A, and the player B would like to minimize v, that is to maximize 1 by v, and what is that is y1 dash plus y2 dash plus y3 dash subject to these constants over here, y1 dash, y2 dash, y3 dash, they are greater than or equal to 0, and this problem D is the linear programming formulation for the player B. Remember here, the problems P and D are dual to each other. So you will call either this as P or this as P, the other will be its dual over here. And further, the problems P and D, the pair of these linear programming problems is the linear programming formulation of player A and B, is the equivalent of the game can be solved using simplest method. So what we do over here, for the player A, you solve the problem P using our simplest method, and then thereafter we can manipulate the things here to get the value of V. What will be V? Equal to 1 upon minimize of x1 dash plus x2 dash plus x3 dash, and thereafter we can get the values of x1 from x1 dash, of x2 from x2 dash, and x3 from x3 dash. In fact, what this is equal to is b into x1 dash is b into x2 dash is b into x3 dash. Likewise, the problem D is the linear programming formulation for the player B, can be solved using simplest method, and then again as we did over here for player A can be done for player B. So an optimal strategy for P1 and P2 can be obtained, rather A and B can be obtained for the given game. Further, because these problems are dual to each other, this optimal value over here is same as this optimal value here over here, which is the reciprocal of the game. Let's solve this game over here using linear programming formulations. Look at here, is the min in the rows over here is -3, is -4 over here, and so what will be max min equal to? Max min will be equal to -3, and what about maximum in the columns is equal to 1 here, 4 here, and 2 here. So min max will be equal to the minimum of all these 3 entries, that is 1 here, and so V will lie between max min and min max, that is equal to -3, is less than or equal to V, is less than or equal to 1, is equal to min max. So we are not sure whether V is negative or not. We need to have, in order to apply linear combinations, linear programming problem technique, V should be positive. So how to make this V positive? Had the entries in this pair of matrix been positive, then we definitely would have V greater than 0. So let's add a number over here. To be on safer side, let's add 5 over here. So if we add 5, just adding 5 to the elements of this matrix, we get here 6 here, 2 here, 7 here, and then 1 here, 9 here, and 3 here. Now this will definitely ensure that the value of this game is positive. In fact, if V dash is the value of this game, then V dash is equal to V plus 5, whatever element we have added over here, and both ways implications that V is equal to V dash minus 5. Now, so instead of writing the linear programming equivalents of this game, we'll write the linear programming equivalents of this game over here, and then we'll solve those games, and ultimately we'll manipulate for the value of the game for the given game using this relation. Now what are the mathematical linear programming equivalents of this game? Let's write that. As did in the previous example, for this game, the equivalent LPP of for the pair P1 will be minimize 1 by V dash equal to x1 dash plus x2 dash subject to these constraints over here: 6x1 dash plus x2 dash greater than or equal to 1, 2x1 dash plus 9x2 dash greater than or equal to 1, 7x1 dash plus 3x2 dash greater than or equal to 1, x1 dash x2 dash greater than or equal to 0. And similarly for player P2, the equivalent LPP will be maximize 1 by V dash equal to y1 dash plus y2 dash plus y3 dash subject to these constraints over here: 6y1 dash plus 2y2 dash plus 7y3 dash less than or equal to 1, y1 dash plus 9y2 dash plus 3y3 dash less than or equal to 1, y1 dash y2 dash y3 dash greater than or equal to 0. These are equivalent to this LPP. Solving these ones, we'll get the results for this one. We'll get V dash for this one, and then V for the given game can be obtained. The optimal strategies over here and over here will be same for the given game also. So in this way we can solve the games using the simplest method over here. But just for simplicity, just to have the simple calculations, we try to add integers or other natural numbers, so that the elements of the matrix, the pair of matrix, becomes positive. So different positive numbers will give us different sets of equivalent LPPs. We can make use of the simplest method to solve a game using this technique over here. Thank you.